All right, this is 6-7, day 2. We just need to finish up for our reciprocal trig functions. Being able to find values, like special values, by thinking about what the graph tells us, and being able to write equations as well. So I'm just going to finish up these last few examples for that. So thinking about secant, cosecant, and then tangent and cotangent. So first of all, let's do some of the special value ones. So we've never gone through ever and memorized any of these secants, cosecants, whatever. So we always think about the reciprocal function and then work with those. So that's really not anything new. This could have been something we did when we did the original unit circle, but they say this now, which is interesting, by referring to the graph of. So thinking about if you graphed infinitely in both directions and just looked at the pattern, what secant was doing, those parabolas opening up and down, what value would you give? So you could just go to a graph and go back to -5 pi and look at the value of the function, which is great. But when we think about our big picture, sometimes it's easier just to look at coterminal and think about it just algebraically. So they say referring to the graph, and you can do that. That's great. But if you don't want to have to make the whole graph, just think about where you would be in the pattern by thinking about that coterminal. So first of all, I'm going to do this as a cosine because I always want to think about the original function and see what that ratio is. Once I know what the cosine ratio is, then I can go ahead and figure out secant of that -5 pi by doing the reciprocal. So I can actually find that and do the reciprocal of that and get my new ratio. So that's what I'm going to be doing. So let's figure out where the heck is -5 pi. My goodness. All right, so where does -5 pi put you? Some of you are getting really good at understanding sort of some of the patterns in this, like the even multiples of pi always ending up at the same thing as 0, because once around the circle is 2 pi. So then the odd multiples of pi must add up on the, or end up on the other side. So let's think about what this would look like. Negative means clockwise. So once around the circle would be -2 pi. Another time around the circle would be -4 pi. And if I go one more pi, that puts me right here at the same as coterminal with pi. So -5 pi is the same location as cosine of pi. So what is cosine there? Well, it'd be -1. I'm going to write it as a ratio. I know that's kind of goofy, but I want you to make sure you understand what's happening here. So cosine of -5 pi is -1 over 1 or -1. To find secant then, I do the reciprocal of that fraction. So 1 over -1, which is going to give me a secant value also of -1, just so happens because it's a 1. So when you flip it, you get the same thing. But you are, in fact, doing the reciprocal then to figure that out. So if cosine had ended up being, say you get an answer for cosine being 1/2, then secant would be 2, right? So you're always doing reciprocal when we think about those. So find something that's coterminal. Think about something that is easier to deal with. So find a coterminal angle to be able to think about what that is. All right, so let's talk about the next one, which is a similar question, really. It actually gets into more thinking about solving an equation. So if we look for values where any trig function is equal to a value, basically what you're looking for are the values of an angle measurement. So you're looking for theta or angles that make this true. Because of the nature of these graphs that they continue infinitely in both directions, we have infinitely many angles where that's going to be true. So that means we have to be able to write those statements and describe all values. So we have ways that we can do that because you can't possibly list them. Once again, though, I never memorized cotangent, secant, cosecant. So instead, I'm going to think of the reciprocal relationship. So if cotangent of an angle is equal to 1, so I'll write it as a ratio, that means tangent of theta would be equal to the reciprocal again of that ratio. Now in this case, the reciprocal of 1, it's still going to be 1. So you're going to be looking for when tangent is 1. So the reciprocal happens to be 1. But what if cotangent was equal to square root of 3? Then that means tangent would have been 1 over square root of 3 or square root of 3 over 3. So we actually do have to flip. I know it's harder to see with a 1, but a lot of the ones that they give you in this section are easy values. So they're looking at 1s and 0s, but this works for any of them. So if you know what cotangent is, rewrite that statement as its reciprocal, so tangent, but just don't forget that you do have to flip the ratio. I know that it doesn't look like you did anything, but you actually did flip the numerator and the denominator. So just like that square root of 3 example would look like. So then your question becomes, okay, when is tangent equal to 1? Well, tangent is equal to +1 in what 2 quadrants? Let's think about that. So it would happen at a 45-degree angle in quadrant 1. And then it would also happen Down in quadrant 3, something else that has a 45-degree reference angle, what would that angle be? Well, that would be 225. So the two places where this would happen would be 45, and then everything that's coterminal with that, all the other things that end in the same spot, we say plus 360k, where k is an integer, and then our other location would be 225 plus 360k. So if you like to have things written in degree form, that's fantastic. I'm going to say, or you could do this in radians. So 45 degrees is the same as pi over what? 4 plus 2 pi k, and then you could say 225 is the same as 5 pi over 4, right? 145 past 180. And that's great too. So that's kind of an either or. Some people notice, and maybe you have thought about this too, that those two sentences can actually be combined into one. So 45 plus 360k and 225 plus 360k are equally spaced. So if you think about where 45 degrees is, 180 degrees later, that's when you get 225. So what if I said this? 45 plus 180k. Would that cover all of our bases here? Well, we'd have every 45 and then 180 degrees later and 180 degrees later and 180 degrees later. It actually is a more succinct statement. So you can write this. It's fantastic. You don't have to. Some people like to have the separate cases, but you could actually, in that case, because they're evenly spaced in the unit circle, you can actually combine them into one. Okay, let's talk about writing equations. All the values that we did yesterday for the shifting up and down, left and right, all of those are exactly the same when we talk about tangent, cotangent, secant, cosecant. The values all do the same things. One thing to be aware of, though, is amplitude. Your textbook doesn't even address the fact that these graphs could still be stretched or compressed. So they're not going to have you think about amplitude, because technically we don't have an A value to put in there because we don't have a maximum or a min. There's no height to the graph. So they don't even mention it. But theoretically, in a question like number 4, they could say write an equation of a tangent function that was vertically stretched by a factor of whatever. And that number, whatever it is, say a factor of 2, so it's twice as stretched out, that would be the number that would go in that A position. So it would still be a 2 up front. Just like if you have a parabola that's 2x squared, it's 2 times steeper. So it works the same way, but your book chooses not to really address that, but just know that those numbers could still be there. So when we write our equations for this, they're not even going to have you deal with an A value because technically there's no amplitude, so they're not going to have you deal with that. K comes next, then parentheses if you have a phase shift, and then our vertical shift. So just kind of some reminders here. So the K, the C over K, that's your phase shift. So if you leave the K value on the outside, it's just X minus the shift. That's kind of a nice way to think of it. So if the shift is negative, that's how you get the minus a negative plus. So it's kind of a nice way to think of that once again. And then there's your vertical shift at the end, but remember it could be at the beginning as well. That's fine too. And then our K value, that tells us something about period. Now here's what you have to be careful with. Tangent and cotangent, for that matter, have a different length of period to start off with. It's pi over K, not 2 pi over K. That's probably the most commonly missed thing here. The original function is only pi long. So be careful when you solve for K. People get really conditioned. We've been thinking about 2 pi over K, and every other graph is 2 pi over K, just not tangent and cotangent. All right, so let's go ahead and solve for that then. It said the period is 4 pi. So 4 pi equals pi over K. Think about what that means and we'll solve the equation. So if your normal graph is only pi long and now it's 4 pi long, that means it's 4 times longer than what it was before. In other words, you would only get through 1/4 of the graph in pi, right? So we'd only have 1/4 of it. So if we solve for K, multiply both sides by K, divide by 4 pi, and be careful when you do this because remember that's 1 pi over 4 pi. So K would be 1/4. You only get through 1/4 of the graph. So the thinking works exactly the same as what it did before. All right, so let's go ahead and put this in here. So Y equals, I would still technically include plus or minus. This graph could still be reflected. If there was some stretch or compression, we'd have that number next, but they're not going to talk to you about that. Tangent of 1/4. Now, do we need parentheses? Well, they say the phase shift is 0, so we don't really have to put that in there. I guess you could say X minus 0, but I don't think that's necessary. And then there's a vertical shift of up 3 or positive 3. All right, so let's try the next one. So we're going to do a secant equation. So secant, important thing to remember there is that when you do the period for secant, that's going to be a 2 pi divided by k. So kind of our general format here once again, and then we can sort of fill in the pieces to see what each thing does. They say the period's 5 pi, so it's stretched out. So period formula for secant, because it's the reciprocal of cosine, would be 2 pi divided by k. So 5 pi equals 2 pi divided by k. Go ahead and multiply both sides by k and solve. And we end up with k equals 2/5. We'd only get through 2/5 of the graph in 2 pi. So again, I'm going to put plus or minus because it could be reflected. If they said somewhere in the problem it was vertically compressed by a factor of, then I would put that number next, and then secant, then my k value, which is 2/5. Now, do I need parentheses for this one? Well, there is a phase shift, so 2 to the left. So that means I'm going to have x minus a negative 2 pi. So it's 2 pi to the left. So it's minus a negative. Left means it's a negative 2 pi. They could have said it that way as well. So that means when you actually look at it, when you simplify, then it's a plus. So minus a negative, that's where that's coming from. And a vertical shift of 3 downward. So if it went down 3, that does mean a minus 3. So when we write these equations, just important to keep in mind what that would look like. You could, if you wanted to, distribute that 2/5 through, and that's fine as well. It just depends on how you want to use that. But definitely for writing the equation, leave the k on the outside so you can just have x minus the shift. It's a much easier way to look at it. All right, and that's the rest of the examples for our day 2. So we should be all wrapped up with section 6-7.